Chapter 8, Lesson 2 on page 224. Today we're learning all about solubility. That's something's ability to dissolve in something. What you'll learn on the left-hand side are our objectives. It says that scholars will explain why water is a good general solvent. Scholars will describe how the structure of a compound affects which solvents it dissolves in. Scholars will identify factors that affect how much of a substance will dissolve. Scholars will describe how temperature affects reaction rate and explain how solute particles affect physical properties of water. Water, the universal solvent. On page 224, in many solutions, including fruit juice and vinegar, water is the solvent. A solution in which water is the solvent is called aqueous, an aqueous solution. Because water can dissolve so many different solutes, chemists often call it the universal solvent. To understand why water is such a great solvent, you must first know a few things about atoms and bonding. Molecular compounds. When certain atoms form compounds, they share electrons. Sharing electrons is called covalent bonding. Compounds that contain covalent bonds are called molecular compounds or molecules. If a molecule has an even distribution of electrons, like the one in figure 7, it is called nonpolar. The atoms in some molecules do not have an even distribution of electrons. For example, in a water molecule, 2 hydrogen atoms share electrons with a single oxygen atom. However, as figure 7 shows, the electrons spend more time around the oxygen atom than they do around the hydrogen atoms. As a result, the oxygen portion of the water molecule has a particular or partial negative charge, and the hydrogen portions have a partial positive charge. The overall charge of the water molecule is neutral. Such a molecule is said to be polar, and the bonds between its atoms are called polar covalent bonds. If you look at the difference between those two pictures on figure 7, you've got 2 atoms that are perfectly sharing in the form of that hydrogen gas. You got 2 hydrogen atoms perfectly sharing those electrons, and then you've got the picture of what looks like an upside down Mickey Mouse. If you look at it, the water molecule that has the larger oxygen and the 2 smaller hydrogens, showing that polarity. There's a certain pole as in a positive and negative charge, even though they're sharing those electrons in that covalent matter. Ionic bonds. Some atoms do not share electrons. When they join with other atoms to form compounds, instead these atoms lose or gain electrons. When they do, the number of protons and electrons within an atom are no longer equal, and the atom becomes positively or negatively charged. Atoms with the charge are called ions. Bonds between ions that are formed by the transfer of electrons are called ionic bonds, and the compound that is formed is called an ionic compound. Table salt is an ionic compound that is made of sodium ions and chloride ions. Each sodium atom loses 1 electron to a chlorine atom and becomes a positively charged sodium ion. Each chlorine atom gains 1 electron from a sodium atom, becoming a negatively charged chloride ion. Our reading check asks us, how does an ionic compound differ from a molecular compound? Well, a molecular compound has what is called a covalent bond, in which there's sharing of electrons. An ionic compound is where there has been a loss or gain of electrons, and now you have a positive and negative charge that's creating that attractive force. Let's review water, the universal solvent so far. Water is the universal solvent. It forms an aqueous solution, and it's called the universal solvent because it dissolves a lot of different things. We're going to see why. Some molecular compounds share electrons in a nonpolar covalent bond. Water is a molecule with polar covalent bonds. Some atoms and compounds lose or gain electrons. Those are called ions. How water dissolves ionic and molecular compounds. The bottom of page 225 and on page 226. Now think about the properties of water and the properties of ionic compounds as you visualize how an ionic compound dissolves in water. Because water molecules are polar, they attract positive and negative ions. The more positive part of the water molecule, where the hydrogen atoms are, is attracted to a negatively charged ions. The more negative part of a water molecule, where the oxygen atom is, attracts positive ions. When an ionic compound is mixed with water, the different ions of the compound are pulled apart by the water molecule. Figure 8 shows how sodium chloride dissolves in water. So sodium chloride, NaCl, is salt. You take salt, pour it into your water. Say you've got a sore throat and you're going to heat up some hot water, pour some salt in there, and then gurgle it to make your throat feel better. Here's an example of how those water molecules pull apart those ions and the solid and turn it into a liquid in that aqueous solution. You'll see that the positive parts are attracted to the negative charges of those ions, and the negative parts of the water molecules are attracted to the positive parts of the ions, so it can dissolve that ionic compound. When an ionic compound is mixed with water, the different ions of the compounds are pulled apart or dissolved by the water molecules because of those attractive forces. Excuse me. On page 226, how water dissolves molecular compounds. Can water also dissolve molecular compounds that are not made of ions? Well, water does dissolve molecular compounds such as sugar. Although it doesn't break each sugar molecule apart, water simply moves between different molecules of sugar. Separating them, like water, a sugar molecule is polar. Polar water molecules are attracted to the positive and negative portions of polar sugar molecules. When the sugar molecules are separated by the water and spread through it, as in figure 9, it shows how they have dissolved. So the water molecules being smaller than the complex sugar, they can actually fit between the different things and spread them out, even though those bonds are still there within the sugar. If you take some water and you want it to be sweeter, or say you're making Kool-Aid, you're going to pour in your 2-3 cups of sugar, pour in your Kool-Aid mix, and then you're going to put in the water. Then you start to stir to dissolve that sugar. That sugar is a molecular compound, and not because it has a positive and negative charge in terms of its ions, but because that positive and negativity comes because it's polar. Because water is also polar, it can dissolve something that is polar because it'll have those attractive forces. What will dissolve? When you stir a spoonful of sugar into iced tea, all the sugar dissolves, but not all of the metal in the spoon does. Why does sugar dissolve in water, but metal does not? A substance that dissolves in another is said to be soluble in that substance, hence why we're learning about solubility. You would say that sugar is soluble in water, but the metal of the spoon is insoluble in water because it does not dissolve readily. Substances that dissolve in another substance are called soluble in that substance. Substances that do not dissolve in another substance are termed insoluble in that substance. Now, what will dissolve in what? Well, it depends on what it's like. The next section it talks like dissolves like. When trying to predict which solvents can dissolve which solutes, chemists use the rule of like dissolves like. This means that polar solvents dissolve polar solutes and nonpolar solvents dissolve nonpolar solutes. Basically saying if something is polar, it will dissolve something that is polar. If something is nonpolar, it will dissolve something that is nonpolar. So it will dissolve something that is just like itself. It has the same or similar properties based on its composition. In the case of sugar and water, both are made up of polar molecules, so sugar is soluble in water. In the case of salt and water, the sodium and chloride ions pair is like water molecule because it has a positive charge at one end and a negative charge at the other end. Reading check. What does like dissolve like mean? Means that the polar molecules dissolve polar molecules, nonpolar molecules dissolve nonpolar molecules. On the other hand, if a solvent and a solute are not similar, the solute won't dissolve. For example, oil and water do not mix. Oil molecules are nonpolar, so polar water molecules are not attracted to them. If you pour vegetable oil into a glass of water, the oil and the water separate into layers instead of forming a solution, as shown in figure 10. You've probably noticed the same thing about oil and water mixtures that make up some salad dressings. The oil stays on the top. Oil is generally dissolved better in solvent than a nonpolar molecule. Nonpolar molecules will not dissolve in polar molecules and vice versa. That oil and water mixture is a really good example of how those things would separate. Well, how much dissolves? Is there a factor that is in play scientifically to determine how much, if we were just to pour sugar in water, would it just keep dissolving all that sugar, or eventually would that water be so full of sugar that it can't dissolve any more sugar? Say we want to make Kool-Aid, but we're not going to follow the recipe, we're going to just load it with sugar. Will it dissolve 10 cups of sugar, or will we have actually solid sugar that we're like crunching on as we're trying to drink that? Probably way too sweet and probably not very good if that was the case. Let's find out. How much will dissolve on page 227? Even though sugar is soluble in water, if you tried to dissolve 1 kilogram of sugar into 1 small glass of water, not all the sugar would dissolve. Solubility is a measure that describes how much solute dissolves in a given amount of solvent. The solubility of material has been described as the amount of the material that can dissolve in 100 grams of solvent at a given temperature. Some solutes are highly soluble, meaning that a large amount of solute can be dissolved in 100 grams of solvent. For example, 63 grams of potassium chromate can be dissolved in 100 grams of water at 25 degrees Celsius. On the other hand, some solutes are not very soluble. For example, only 0.00025 grams of barium sulfate will dissolve in 100 grams of water at 25 degrees Celsius. When a substance has an extremely low solubility like barium sulfate does in water, it is usually considered insoluble. So different things dissolve differently based on their molecular structure or how their atoms are put together. Solubility in liquid solid solutions. Did you notice that the temperature was included in the explanation about the amount of solute that dissolves in quantity of solvent? The solubility of many solutes changes if you change the temperature of the solvent. For example, if you heat water, not only does the sugar dissolve at a faster rate, but more sugar can dissolve in it. However, some solutes like sodium chloride and calcium carbonate do not become more soluble when the temperature of water increases. The graph in figure 11 shows how the temperature of the solvent affects the solubility of some solutes. A lot of times if you are going to increase temperature, you're going to increase solubility because that increased temperature actually increases the motion or the movement of those molecules, therefore causing the different types of reactions to take place for that to be dissolving. For example, if it's cold outside at this time of the year and you want to make hot chocolate, you can pour hot chocolate into a cold glass of water and then try and stir it up, but some of that hot chocolate might not actually dissolve. But when you put it into the microwave and start to cook it, you heat it up, increase that temperature, increase that motion, then you stir it, it actually starts to dissolve because of that temperature that increases the ability for that item to be soluble. Solubility in liquid gas solutions. Unlike liquid solid solutions, an increase in temperature decreases solubility of a gas in a liquid solution. You might notice that if you ever opened a warm carbonated beverage and it bubbled out of control while a chilled one barely fizzed. Carbon dioxide is less soluble in warm solution. What keeps the carbon dioxide from bubbling out when it is sitting at room temperature on a supermarket shelf? Well, when a bottle is filled, extra carbon dioxide gas is squeezed into the space above the liquid, increasing the pressure in the bottle. This increased pressure increases the solubility of the gas and forces most of it into the solution. When you open the cap, the pressure is released and the solubility of the carbon dioxide decreases. So pressure can be another factor that influences how much something dissolves at. But in the case of temperature, if you're at a lower temperature, there's actually less gas that dissolves in a liquid. So when you have a warmer soda, sometimes it'll make that sound and it'll be really, really loud. If it's colder, maybe it makes a little bit less in terms of that actual dissolving inside of that solution. Reading check. Why does a bottle of carbonated beverage go flat after it has been open for a few days? Well, that's because there's less pressure. And if there's no pressure in this case, that pressure is another affecting rate of dissolving. If there's no pressure, then it doesn't stay in that liquid and actually can come out of that liquid. So it's undissolving or coming out of that liquid in that case. Saturated solutions. If you add calcium carbonate to 100 grams of water at 25 degrees Celsius, only 0.0014 grams of it will dissolve. Additionally, calcium carbonate will not dissolve. Such a solution, one that contains all of the solute that it can hold under a given condition, is called saturated solution. So back to our question before. Could you take and make this Kool-Aid recipe with tons and tons of sugar, like the whole bag of sugar? Eventually, the sugar will stop dissolving because the solution is considered saturated. Figure 12 shows a saturated solution. If a solution is a liquid solid solution, the extra solute that is added will settle to the bottom of the container. It's possible to make solutions that have less solute than they would need to become saturated. Such solutions are unsaturated, and an example of an unsaturated solution is one containing 50 grams of sugar and 100 grams of water at 25 degrees Celsius. That's much less than 204 grams of sugar the solution would need to be saturated. So that's why our recipe for Kool-Aid has some sugar in it, but it doesn't have a ton, because eventually that sugar is not going to dissolve anymore. Okay? A saturated solution contains all the solute it can hold under a given condition. A hot solvent usually can hold more solute than a cool solvent. When a saturated solution cools, some of the solute usually falls out of the solution. But if a saturated solution is cooled slowly, sometimes the excess solute remains dissolved for a period of time. Such a solution is to be called supersaturated because it contains more than the normal amount of solute. So if you want to get over this issue and you want to make yourself some Kool-Aid that has way extra sugar in it, what you need to do with your water when you're trying to get your sugar to dissolve in it, don't put the Kool-Aid mix in yet, but if you heat that water up, then more of that sugar will dissolve because the higher temperature increases the movement of those molecules and there's more of this solubility or the dissolving that takes place. Then you cool it back down slowly, and when it cools down slowly, more of that sugar will stay in it. If you just pour a bunch of sugar into the water and try and stir it up, it'll actually leave sugar at the bottom of that beverage. It's not going to be very good. But if you heat it up, add more sugar, and then cool it back down slowly, that sugar will stay in there. It'll be called supersaturated in that case. The rate of dissolving and concentration. Solubility does not tell you how fast a solute will dissolve. It tells you how much of a solute will dissolve at a given temperature. Some solutes dissolve quickly, but others take a long time to dissolve. A solute dissolves faster when the solution is stirred or shaken, or when the temperature of the solution is increased. Sorry, let me go back a slide here. Here are some of those factors again. Time, motion, temperature, constant area affecting the rate of dissolving. These methods, a solute dissolves faster when the solution is stirred or shaken or when the temperature of the solution is increased. These methods increase the rate at which the surface of the solute come into contact with the solvent. Increasing the area of contact between the solute and solvent can increase the rate of dissolving. This can be done by breaking up the solute into smaller pieces, which increases the surface area of the solute that is exposed to the solvent. So any type of motion, any type of temperature, or increasing that surface area increases the number of those interactions that can then take those polar molecules to attach to polar molecules and nonpolar molecules to attach to nonpolar molecules and increase that dissolving or increase that rate of dissolving. Some solutes become more dissolvable at that time, and an increase in temperature usually is a decrease of that gas solution, but in this case, we're talking about what increases that rate of dissolving. Molecules are always moving and colliding. The collisions must take place for chemical processes to occur. Chemical processes take place at a given rate of reaction. Temperature has a large effect on the rate. The higher the temperature, the more collisions occur, and the higher the rate of reaction. The opposite is also true. The lower the temperature, the less collisions occur, and the lower the rate of reaction. Refrigerators are an example of slowing the rate of reaction, and therefore the chemical process down to prevent food spoilage. So the rate of dissolving again is influenced by time. More time usually means more dissolving, or in the case of your soda going flat, the opposite. If you've got more motion, like you're shaking or stirring something, it'll dissolve better. If you've got a higher temperature, it'll dissolve better because there's more movement of those molecules. And the content area, as in the surface area, if you break something down into smaller pieces, for example, let's say you left your sugar out and it dried out and it's in these big clumps. If you break it into smaller pieces, there's more surface area for that to actually dissolve in. So all those factors included affect the rate of dissolving. Concentration on page 229. Concentration of a solution is how much solute is present compared to the amount of solvent. What makes strong lemonade strong and weak lemonade weak? The difference between the two drinks is the amount of water in each one compared to the amount of lemon. The lemon is present in different concentrations in the solution. The concentration of a solution tells you how much solute is present compared to the amount of solvent. You can give a simple description of solute's concentration by calling it either concentrated or dilute. These terms are used when comparing the concentrations of two solutions with the same type of solute and solvent. A concentrated solution has more solute per given amount of solvent than a dilute solution. For example, Mr. Shane makes lemonade in class, and he would share this with you. He would make one with 5 cups of sugar, and you would taste it and say, wow, that's really, really sweet. He'd make another one with 2 cups of sugar, and then he'd pour another gallon of water into it to make it so you could barely even taste the lemonade. One of those you would say is a concentrated solution because it has a lot of that sugar and a lot of those ingredients. One is a diluted solution because more water has been added to it. It's a more aqueous solution, therefore lowering that overall concentration. How do you measure concentration? Can you imagine a doctor ordering a dilute intravenous or IV solution for a patient? Because dilute is not an exact measurement, the IV could be made with a variety of amounts of medicine. The doctor would need to specify the exact concentration of the IV solution to make sure the patient is treated correctly. So you have to know concentrations of items in order for you to have the proper level of those things when you're talking about medicines or ingredients, those types of things. One way of giving the exact concentration is to state the percentage of the volume of the solution that is made up of the solute. Labels on fruit drinks show their concentration, like the one in figure 13. When a fruit drink contains 50% fruit juice, the remaining 85% of the drink is water and other substances such as sweeteners and flavorings. The drink is more concentrated than another brand that contains 10% fruit juice, but it's more dilute than pure juice, which is 100% juice. Another way to describe the concentration of the solution is to give the percentage of the total mass that is made up of the solute. So if you look at the back of anything that you're drinking and it gives you the percentage of what it's made up of, in this example, it's talking about cranberry apple juice. It says this percentage of juice, the rest is water. It's showing you what that overall concentration of that solute is that is inside the solvent. Again, water is the solvent in that aqueous solution. Effects of solute particles on page 230. All solute particles affect the physical properties of the solvent, such as its boiling point and freezing point. The effect that a solute has on the freezing or boiling point of a solvent depends on the number of solute particles. When a solvent, such as water, begins to freeze, its molecules arrange themselves in a particular pattern. Adding a solute, such as a sodium chloride salt, this solvent changes the way that the molecules arrange themselves. To overcome this interference of the solute, a lower temperature is needed to freeze the solvent. So salt water actually freezes at a lower temperature than fresh water. Because the salt water has salt dissolved in it, it changes the molecular compound of that water, the molecular composition, and therefore it has a lower freezing point. So fresh water around here in Wisconsin, the lakes and things like that would freeze at 32 degrees. The larger body of water, such as the ocean, freezes at an even lower temperature than that freezing point of fresh water. When a solvent such as water begins to boil, the solvent molecules are gaining enough energy to move from a liquid state to a gaseous state. When a solute such as sodium chloride is added to the solvent, the solute particles interfere with the evaporation of those solvent particles. More energy is needed for the solvent particles to escape from liquid, and the boiling point of the solute will be higher. So just like it would take the freezing point and make it lower, it also takes the boiling point and makes it higher for a solution, because those molecules of what is dissolved inside that solution interfere with that natural interaction or that natural change of state. So you have a higher boiling point and a lower freezing point normally when something is dissolved within that aqueous solution. We finished our reading for today, and I want to take a look at our assignment in the form of our reinforcement. Here's our reinforcement. It's all about solubility. The directions say write true in the blank if the statement is true. If the statement is false, replace the italicized word with a word or term that makes the statement true. Write this new word in the blank. Let's get started. Number 1. In the water molecules, electrons are equally shared by hydrogen atoms and oxygen atoms. We'd say that's false because we know that it's not equally, it's unequally. That's why it's a polar molecule. Number 2, solutions for which water is the solvent are called aqueous solutions. That's true. Number 3, if electrons are shared equally between atoms that compose a molecule, the molecule is said to be polar. Again, polar is unequal, so they're trying to drive that answer home for us, that polarity means unequal sharing of those electrons. Number 4, water readily dissolves most polar compounds. It's true. 5, table salt, NaCl, sodium chloride, is a molecular compound. False, that's an ionic compound because of the loss and gain of electrons between those two. Number 6, in an ionic compound, one or more atoms loses electrons and one or more atoms gains electrons. Well, we just use that number 5 as an example, so 6 is true. 7, in a solution, the charged regions of water molecules can pull an ionic compound apart. 7 is true. That's why it's called the universal solvent. Even though water is polar, it can dissolve some things that are ionic because of that positive and negative charge. 8, chemists say like dissolves like. This means that dissolution tends to occur when the solid and the solute are similar in nature. 8, we're not going to say that this italicized word solid and solute are similar. That word would be solvent. Like dissolves like. This means that dissolution tends to occur when the solvent and the solute are similar in nature. Okay? Number 9, most oils tend to dissolve best in nonpolar solvents. Number 9 is true. Number 10, solubility tells you how fast a solute will dissolve. False. Tells you how much a solute will dissolve. Doesn't tell you the rate. We notice that there are different things that affect the rate, but doesn't tell you the rate that it's actually influenced by. It tells you how much of that solute will dissolve. That's our solubility measurement. Directions for 11 through 16. Answer the following questions on the lines provided. 11. How is the solubility of a substance usually described? Well, if you think about something's solubility, to say, will this dissolve or will it not dissolve? So the scientific measure is how much of this will dissolve in 100 grams of solvent at a given temperature. So science adds in that you need a specific concentration and you need a given temperature for that solubility, because if you have a different concentration, you have a different dissolvability or solubility, and if you have a different temperature, you have a different dissolvability, because those are factors that influence that. So again, for number 11, how much solute dissolves in 100 grams of solvent at a given temperature? Number 12, what is an unsaturated solution? This is a solution that can dissolve more solute, as in it can take in more things. So if you're stirring up your Kool-Aid, you put in 2 cups like it recommends, you think that's not enough, I'm going to pour in more, but it's not to the point where we've got sugar that's still in the bottom of our pitcher. It's actually a little bit less than that. 13, how can a solution become supersaturated? Here was our example. If we wanted to overload sugar into something, we'd actually have to heat it up. If you increase the temperature, you increase the ability for a solvent to dissolve something, and then you slowly cool it down, and some of that dissolved sugar would actually stay in the solution and become supersaturated. Number 14, what happens if you continue to add solute to a saturated solution? Eventually, it stops dissolving. It will not dissolve anymore past the saturation point. 15, can pressure affect the solubility of a substance in a solution? Yes. It increases the amount of gas that can be dissolved in a liquid. So why is your soda can, bottle, 2-liter bottle always sealed, and as soon as you open that, it makes that sound? Well, because the pressure of when that was packaged the first time was added into it. There's actually extra gas that's pushed into that liquid so that it dissolves and actually preserves that for a longer period of time. If you open that, that's when your soda goes flat. 16. How does temperature affect the solubility of a solute in a solvent? The amount of most non-gaseous solutes that can dissolve in liquid solution rises with temperature. So if it's not a gas that we're talking about here, if it's a liquid-solid solution or liquid-liquid solution, a lot of times temperature increases solubility. The opposite is happening when it's gaseous. There's actually less that dissolves at a lower temperature just because there's less of that interaction. Hope that helps you with completing your reinforcement. Thanks for following along. God's blessings.